squared. You end up with a t-value of 11.124. Now, if we say that we're interested in does that 11.24 fit for a 95% confidence interval, again, t with 16 minus 2 degrees of freedom, and you look that up in the table, and you see that that t-value for alpha over 2, so alpha being 0.05, alpha over 2, 0.025, look it up in the table for 16 minus 2 or 14 degrees of freedom, and indeed 11.124 is not between those two values, so therefore we can conclude that there is a linear association between x and y. Therefore, we can progress to regression analysis and say, okay, well, if you know, again, let me see if I can pull that back up. Where's that picture? There it is. You know, just eyeballing it quickly, yeah, it looks like there might be a linear relationship. Now the next question is, we've done the quick test on the t, we've calculated sample correlation coefficient. We have done the quick t-test, and it fell outside of it. And so the third step is regression. So the question becomes, what line is the best fit for this relationship? And let's go take a look at what that means. Regression analysis. We're going to look at some simple linear regression. The statistical analysis used to investigate and draw conclusions about functional relationships existing between a dependent variable and one or more independent variables. Okay. So we have the case that y was the dependent variable, x was the independent variable. We could think about it, and this is the full form of a multiple regression model, y being the dependent variable or the response variable, and then you have all these x1 through xk independent variables. And what we have is we're looking for a linear, what would be the true linear relationship that exists between y and all these other different variables. And what we don't know are what are the best values for betas, beta naught, and then the coefficients beta 1 through k, associated with each one of those random variables, x1 through xk. And also what is the experimental error epsilon. Simplifying this, a simple linear regression model, looking at just what we had with the tread tire example previously, dependent variable y, there is some beta naught and a beta 1 coefficient for each value of x and an epsilon. And turns out that epsilon, that error, follows a normal distribution with a mean of 0 and a standard deviation of sigma. The data, we're working with that pairs of data. In the previous example, we had a pairing x1, y1, x2, y2, and we had that all the way out to x16 and y16. We had 16 pairs of data, x and y. So what we have here is, again, there's a true value of beta naught and beta 1, in this case, that we would like to have, but we're, again, going to use our sample data to come up with estimates. What's the best estimate for beta naught? And we're going to be using, this is the formula that you would use to apply to your sample data to come up with those estimates. So if we have a true regression line, is y is equal to beta naught plus beta 1 times x plus an epsilon, then the least squares point estimate of this y hat is this little b, which we're using as a point estimate for beta naught, and we're deriving it again. Beta b1 and b naught are being derived from our sample data. So b1 is the point estimate for beta 1. The data used for illustration are from a study of two methods. Okay, this is what I had a minute ago. We're going to use that same set of data. Okay, so those different points of x and y values, 16 different values. To calculate the regression line, to calculate these point estimates B0 and B1, we plug in the values, going back to slide 17, plugging into here all these different values, 16 different values, pairings. We're going to plug them into here to get estimates for values for B0 and B1. And these are just some computational things that you can verify for yourself. You come up with values of B0 and B1, which are our estimates for beta naught and beta 1. Turns out that beta naught is 13.5, and the B1 is going to be 0.79 roughly. And so what we have is an estimate, a line estimate, values estimates B0 drawn from our sample. We used our sample data, B0 and B1, our estimates for beta naught and beta 1, the true straight line that could be applied for if we had all the values associated with X and Y. And we're using our sample that we've drawn as to derive these estimates, to fit a line basically to this set of points that we have. Okay, if you go back to the course Blackboard, and you'll see some exercises I've proposed from there, from your textbook that you could work on to practice a bit of this. This is just, and we're going to talk about this more in class, obviously, when we're face-to-face, but this is just a very brief blast into the chapter that talks about correlation coefficients and covariance, those topics, as well as this idea of regression analysis. Noted a possible linear relationship between two variables, looked at least squares point estimates for approximate relationship, to approximate the relationship. Again, those B0, B0, and B1 were point estimates for the beta naught and the beta 1, which would have been the true regression line. You could take each one of those, just as we have for, we drew a sample mean, or we drew a sample, we took the sample mean, we came up with a confidence interval using that sample mean information. You do the same thing here for your beta, for your B0 and B1 that you derive from your sample. Come up instead with confidence intervals, with what's the probability, what's the confidence interval around B0 such that with 95% confidence, we believe that beta naught, the true regression line value parameter, would fit in that confidence interval that's derived again from your sample data. So we didn't look at that, but that is kind of where this leads. Analyze the quality of the estimated regression line. Analysis of variance. That's a whole other area of statistics that you get into. What's the quality of the regression line that you've generated? This is linear. As I mentioned, and again, when we're face-to-face in class, I'll show you a couple of websites. I'll show you a couple of software companies that are selling this type of software that is commonly used in businesses and large organizations to understand relationships, to create linear and nonlinear regression function, to look at the relationship between different variables and then fit the corresponding either linear or nonlinear functions to those relationships. So, but this was just a brief glance into it, and I'll wrap up here. So we'll see you in class.